Well, hello, thanks for watching. I'm going to create this video to try to help you relate some of the ideas that you've seen earlier, which are force, work, potential energy. Those things really tend to get muddled together sometimes, and I know at least in our textbook, it's not the best presentation. So I'm going to try to show you maybe a real physical example you could picture and talk about what's going on using the language of work and energy and forces. So we'll just start with I think a pretty simple example of somebody that's raising a box upwards. So this can just be somebody maybe lifting a mass. We'll give it a mass of M. And let's just say that we are looking during the part of the motion where the object raises up some particular height. We'll just call that H. So what's going on here? Well, from a force perspective, let's give this person a name. How about Chris? Keep it somewhat gender neutral. So Chris has to exert a force on the box in order to lift it up. And what is the force that Chris will have to use? Well, that, of course, is just equal to the weight of the box. So Chris exerts an upward force, while gravity is exerting a downward force, and if it's moving at a nice steady speed, there's no net force, and therefore it's not going to accelerate. And so that's how we examined it from the Newton's second law kind of perspective. But what about the work-energy perspective? Well, let's calculate or write expressions for the amount of work that's being done on the box as it's being lifted up. And when you talk about the work being done, you always have to specify the work done by what? By a particular force, because every work is associated with a particular force. Now you could, I suppose, talk about the total amount of work done, which just means figure out all the little parts of the work and then add them all together. And we did that with forces as well. The nice thing about work is we don't have to worry about directions. It's not a vector. Although we can have pluses and minuses, it's still going to be adding up something like on a calculator. You don't have to get vector directions involved. So if we say the work done by Chris, that means the force Chris exerts times the distance through which Chris exerts that force times the cosine of the angle in between those two directions. Well, what would that be in this case? Well, as we pointed out, Chris's force is just going to be equal to mg, that's the weight of the box, and the distance would be that height that we've covered, and the cosine of what? Well, in this case, both the motion and Chris's force are in the same direction, and so that would be the cosine of 0. We don't need to include the cosine of 0 because it's just equal to 1. So mgh would describe the work done by Chris. But of course, there's also work done by gravity at the same time. And this would be the force of gravity times the distance covered while that force was acting times the cosine of the angle between those two forces. Well, what would that be? That would be, of course, force of gravity is also mg. The distance covered is h. But now look at theta. The angle between the force direction and the motion is not 0, but 180, because the force of gravity is straight down and the motion is straight up. So that just introduces the cosine of 180, otherwise known as -1. So that accounts for all the different forces, and therefore all the work acting on the box. Or we don't say work acting, we say work done on the box. So then there's this important theorem known as the work-energy theorem, and it says if you account for all of your forces and you total up all the work done by those forces, that should always equal the change in kinetic energy of the box. Well, what do we get here? Total work is mgh minus mgh, which is 0. And isn't that also equal to the change in kinetic energy of the box? We're moving at a steady speed. We know that because we specified that we weren't accelerating it. We were trying to keep Chris's force just equal to the gravity force. And so this relationship actually is pretty easy to see here. Here's where students get confused, though. They say, wait a minute, shouldn't work equal the total energy change of the box? Because clearly you can see that the box is higher than when it started out. So what about the potential energy? Well, the work-energy theorem only deals with the total amount of work done equaling the change in kinetic energy. If one of those forces happens to be gravity, then there will be a change in gravitational potential energy, because that's what the work done by gravity does. It changes potential energy. If we had a spring involved, we could have work done by a spring, and it would also change the spring energy. And what is that relationship? Well, here's another important relationship. The work done by one of those forces, that could be gravity or springs, is equal to the negative or the opposite of the change in potential energy. So I've got to use some language here. First of all, we only talk about potential energy for certain kinds of forces. Those are the kinds of things where we can store energy. That's why we call it potential energy. The two that we've seen so far in mechanics are gravity and springs. We do not store energy in the form of friction. We don't store energy with Chris's force. We don't store energy with normal forces or tension forces. Those don't have that same kind of property. So those forces that allow us to store energy are known as conservative forces. That's actually where we get the term conservation of energy. Energy is not conserved if we have some non-conservative forces, things like friction or tension forces, because suddenly it seems like, hey, where did the mechanical energy go? And this thing was moving nice and fast, and now it's not moving at all. Well, that might be because there's some friction involved, a non-conservative force. So you can't conserve energy with those kinds of forces. So this only holds true for conservative forces. Now, there are other conservative forces that we will encounter in our other classes. The electric force, for example, is a conservative force. But I don't want to get into electricity or magnetism at this point. Let's just say gravity and springs. Those are the only two conservative forces we have to deal with. So there's a nice relationship. Some other connections we can make with this. I think I'm going to start a new page, because we've done some things with work that I'd like to tie in. And I'm just going to write this relationship again, a little differently though. I'm just going to move the negative to the other side. So we've got three different ways that we've examined so far work. And this could be, work was force multiplied, or technically dotted with, some displacement. Now I'm going to use the generic symbol R here. Could be horizontal, which we usually mean X, or if it's vertical motion, we usually use Y. But I'm just going to use the generic symbol R. So if I put the negative on there, now I've got a way of describing the change in potential energy. Now again, this has to be a conservative force for this to work. This could also be the area under a force versus distance graph. This could also be, that's the negative of that. This could also be the negative of the integral of force over some distance, dr. This would have to be between, some beginning and ending point. We'll call it R1 and R2. Again, you won't typically see this written as an R, but you'll see it written with X's and Y's. So all three of these forms work fine for calculating the work, and now we know for conservative forces, they'll work great for calculating a change in potential energy. The only difference is you throw a negative sign on, or maybe take a negative sign off. It works great. So that's a nice relationship to use. Sometimes you'll get a potential energy curve. If you get a potential energy curve, sometimes you're going to be asked about a force. Well, if we take this relationship here, I'm just going to rewrite it. Delta U divided by R, the negative of, is equivalent to a force. You see, that's just a change in the order that I wrote these. So what is this? Well, this might be the slope of a potential energy versus distance graph. So something like this, potential energy versus, again, X or Y. I'll just put R here. So we could have some sort of oddball curve like that. At any point, if we calculate the slope, that might be a derivative in some cases too. That gives us a measure of the force. That's if we take the negative of it. I often forget the negative sign. That's something that students do too. Not a huge thing, but it's something you want to try to work on. So the negative of the slope will give us a measure of the force. So this idea here, and actually let's write it in the calculus version, du dr. That relationship there and this relationship here are actually kind of inverses of each other. I guess technically this one here. Those are inverses of each other. And you're used to inverses like squaring and square rooting. You know those. Or taking a sine versus an inverse sine. Well, this is taking a derivative versus taking an integral. It's just a different math for you maybe to get used to thinking of those as inverse or opposite kinds of operations. But might be helpful to remember that. On the AP reference sheet, you're going to not see all of these. I believe they tend to write the work-energy relationship in this form here. So if you get used to seeing that and then recognizing, oh, I could write that in the opposite order and this, then you'll remember perhaps things like that's a slope, or maybe just the derivative of the potential energy. So all kinds of different forms that can take. But I think that's enough here. That's gone on over 11 minutes, and hopefully you got enough to kind of get you through whatever problem you're facing. Of course, you see me or your teacher, whoever that is, if you need more help than that. Thanks for watching.